Hello everyone, welcome to our talk. This is Xiaochen from University of Technology Sydney. This is a joint work with Guanqing, Haoyu, and Yulei. This talk will present a new path-sensitive code embedding approach called Contraflow, which leverages precise path-sensitive value flow analysis and recent advanced self-supervised contrastive learning to significantly boost the performance and reduce the training costs of path-based vulnerability detection. Software vulnerabilities have been rising dramatically during the past few years. It acts as a major concern in the development of reliable modern software systems. There are several static bug detectors, including open-source analyzers like Infer, SVF, Flowvender, and also some commercial tools like Checkmarx, Cavity, Cobalt, and Pinpoint. They basically rely heavily on user-defined specifications and domain knowledge to detect different types of vulnerabilities, making them label-intensive. They also have difficulty in finding a wider range of vulnerabilities, like naming issues and incorrect business logic. The recent success of deep learning techniques has opened new opportunities to develop more intelligent detection systems. Given the source code as inputs, the neural networks can learn vulnerability patterns that capture the correlation between vulnerable programs and their extracted code features. Existing learning-based detectors basically use code embedding, which aims to represent code semantics through distributed vector representations to represent the input source code. The well-trained model can then predict whether the code vector is vulnerable or safe. Initially, the embedding approach treats a program as lexical tokens and apply natural language processing techniques like recurrent neural networks to learn code semantics without considering code structure information. Later, several approaches improve the embedding results by preserving structure information, for example, through program dependence graphs, and then use graph neural networks GNNs to classify whether a graph or subgraph of a code fragment is vulnerable or not. Existing models are still insufficient for precise bug detection because the objective of these models is to produce classification results rather than comprehending the semantics of vulnerabilities, like pinpointing bug triggering paths, which are essential for static bug detection. Let's take recent advanced graph-based approaches as an example. In general, the graph features are learned from message passing between all connected node pairs. For example, the feature vector or message of node I is passed to its neighbors, nodes J1 and J2, through their connected edges. A graph representation is insufficient for path-based vulnerability detection because the graph neural network does not distinguish feasible or infeasible program dependence paths. The message passing in GNN is path insensitive. For example, we have two edges 1 to 2 and 2 to 3 labeled with a contradictory transfer condition, C and next C respectively. According to the definition of GNN's propagation rule, the feature vector of node 1 will be passed to node 3. However, in principle, the information cannot be propagated through this infeasible path because the control flow transfer condition is violated. GNN's message passing is also context insensitive. For example, we have two paired call size and return size here. The feature vector of node 1 will be transferred to node 2 and then goes to node 3, which clearly violates the principle of context sensitivity. To address the above limitations, the detection approach is expected to work on a precise learning model that can preserve value flow paths. Some recent code embedding approach embed a bag of paths on abstract syntax trees, ASTs, or value flow graphs, or VFGs. These approaches mainly aim at code classification and summarization tasks. They cannot be directly used for sophisticated tasks such as path-based bug detection due to a potentially unbounded number of program paths which need to be embedded. The effectiveness of the path-based code embedding lies in two aspects. First, the path embedding model needs to precisely preserve the in-depth semantics of paths. Second, the path selection strategy needs to preserve individual feasible paths with discriminative features which contribute to bug semantics during model training. We present Contraflow, a path-sensitive code embedding approach which uses self-supervised contrastive learning to pinpoint vulnerabilities based on value flow passes. The inputs are unlabeled program and the program labeled with vulnerability tags. We first generate value flow passes using an existing static analyzer (SVF). Based on the unlabeled code fragments, we enable contrastive learning to pre-train a value flow path encoder or VPE, which can produce the vector representation of each value flow path. Our contrastive learning is self-supervised and does not need manual labels to capture the deep semantics of passes. The resulting VPE is then used to guide the path selection process through self-supervised active learning by reducing the substantial number of value flow passes. We also introduce sparse and guarded value flow analysis into code embedding to further refine the selected value flows by checking their path feasibility. These selected passes are then used for training the downstream fine-tuning task, vulnerability detection, based on the program with vulnerability tags. After training, our vulnerability detection is then able to report likely buggy passes of a non-SIM program based on the path-sensitive representation and report important value flow passes contributing to a vulnerability. Next, let's go through these three phases using a motivating example. Here is a real-world vulnerability from POCO. It is caused by the API misuse when calling the API set status after rebuild list, where the variable HD is first defined at 9.2, then modified at 9.6, and used at 9.13. This buggy value flow path of HD can cause unexpected behavior and result in denial of service. The input of phase A is a bag of value flow passes extracted from the code fragment, like pi1 to pi4. The number in the circle represents the non-number. Each value flow path consists of a sequence of program statements representing a defined use train between variables, with the guard on each edge between two statements to indicate control flow transfer conditions. For example, there is a flag at edge 226, indicating that line 2 can reach line 6 only if flag is true. We use the value flow path encoder or VPE to transform a value flow path into its semantic vector. The VPE consists of two components, a local encoding which captures the local feature of each statement, and a global encoding which preserves the global feature of the entire path. For the local encoding, we leverage a graph neural network to encode the syntactic structure information of the AST subtree of each program statement. The feature vector of each node comprises two parts, node token and AST node type. For example, the node N2 is of type Coli and has a token rebuild list. We use word embedding to produce their corresponding vectors. The global encoding models the sequential naturalness of the long-range defined use train on a value flow path by leveraging bidirectional gated recurrent unit and the attention mechanism. We feed all the passes into the VPE twice using different dropout masks to obtain their vector representations and corresponding contrastive representations. VPE is pre-trained using contrastive learning by minimizing the noise contrastive estimate loss to capture the semantics of value flow passes, such that the pre-trained similar embedding vectors like pi1 and pi1 plus stay close to each other, while dissimilar pairs like pi1 and pi3 plus are far apart. This phase does not require any human annotation and is trained in a self-supervised manner based on a large number of unlabeled value flow paths. The pre-trained VPE will be used in the next two phases. In phase B, we first sample a proportion of representative value flow passes, like pi1 to pi4, according to the rankings learned from self-supervised active learning. These passes are further fed into the path feasibility tracking to remove infeasible value flow passes based on the value flow gas. For instance, path 3, 9, 13 is infeasible because the control flow gas neg flag at 3 to 9 and flag at 9 to 13 contradict with each other. Similarly, path 2, 6, 15 is infeasible because the control flow gas flag at 2 to 6 and neck flag at 6 to 15 contradict with each other. We will exclude these two infeasible passes in the next phase. Finally, in phase C, we use the vectors of the selected feasible and representative value flow passes produced by phase B, which are generated by the VPE model transferred from phase A. These embedding vectors then go through a transformer architecture based on multi-head self-attention to produce a contextual vector for each value flow pass. For example, the contextual vector of pi1 is computed by attention with the other vectors, like pi4, to aid their influence on pi1. After this, a soft attention layer is applied to merge these contextual vectors into one vector, which is used for training the detection model. The ranked attention weights indicate the contribution of different value flow passes to the model output. For instance, the value flow pass pi1 possesses the highest attention weights, 90%, while the others are negligible, indicating that this value flow pass is likely a buggy pass. We evaluated control flow using 288 real-world open-source projects extracted from 3 existing datasets, which are either built upon public CVEs or labeled by domain experts. We label a sample as vulnerable if it contains at least one vulnerable statement, and safe otherwise. In these projects, we extracted over 2 million program methods and over 11 million slices for our experiments. 80% of them are used for training, 10% are used for tuning, and the remaining 10% are used for testing. We compare control flow against 3 recent method level tools: Widget Detector, Division, and Review, and 5 recent slice level tools: Bondi Packer, CCVR, Deep Wukong, Bondi Locator, and IV Detect. This table shows the comparison results under informedness, markedness, F1 score, precision, and recall. Control flow outperforms all our baselines with an average improvement of F1 score at around 22.9%. This figure compares the average vulnerable rankings at 1 to 20 and average safe rankings at 1 to 20 of these approaches. It is clear that control flow achieves the best average vulnerable and safe rankings across all the ranges. We also compare with 2 fine-grained baselines, IV Detect and Bondi Locator, in terms of locating buggy statements. There is still an average gap of approximately 15.4% mean intersectional union and 24.6% mean statement F1 score between these 2 approaches and control flow. This table also shows the fine-grained comparison, and control flow clearly performs better than our baselines. For example, the statement accuracy at 12 LOS is the largest, at 84.1% for control flow, and control flow improves Bondi Locator in terms of mean first ranking and mean average ranking by 4.8 and 4.7 ranks, and IV Detect by 2.3 and 2.2 ranks, respectively. We also conduct an ablational analysis to evaluate 4 important properties in control flow, namely contrastive learning, path sampling, path sensitivity, and different VPEs, to further understand their contribution to the final results. Overall, control flow with all the best properties combined performs better when one property is disabled or replaced. For the non-contrastive version, both the informedness and markedness dropped to below 62% from over 72%. Path insensitive control flow reports a significant gap of 20.6% for F1 score and 53.3% for mean intersection over union. The performance of different encoders called BERT, BLSTM, and BGRU is also worse than our VPE. This figure shows the data sensitivity analysis with or without contrastive learning. The non-contrastive version of control flow records a sharper decline by nearly half of the F1 score and more than half of the mean intersection over union to below 10%, while the F1 score for control flow's contrastive version drops from 70.5% when using the full dataset to 59.6% when using only a fifth of the dataset. Thank you all for your time, and I am happy to take any questions.